I think technology is very important, but there's a vast knowledge base now, and so there are often experiments that you can do which take items of knowledge from different areas, and then you can often do a very simple experiment that uses technology from 10 years ago. So it needs a combination of developments of new technology that open up new ways of doing it. And of course what we've been doing with electron cryomicroscopy is an example of that technology. But the technology, for example, of DNA sequencing and the genome, so 17 years ago we had the human genome, now there are hundreds of thousands of human genomes. So there's vast amounts of data in databases that haven't really been extensively analyzed. So you can have a combination of deep thinking, use of existing information, as well as the technological advances of the future. So I think you need to have a distillation of all the information from different sources. Taking the technology of electron microscopy that had been developed often by the people who were working on metallurgy or material science, who were pushing the resolution. So we had the advantage of being able to bring equipment from that direction in, but then there were other problems that the material scientists did not have. We wanted to have cold stages. Often they want room temperature or hot stages. And then once we develop these cold stages, or pressurize the manufacturers into developing cold stages, although we have done some of them ourselves. Often then you find the material scientists say, okay, these are very useful. So I think people who work on lithium battery technology, for example, find that some of these cryomicroscopy methodologies are quite useful. So you need to have, I think, both of the taking techniques that have been invented in one area, moving them over and adopting them in other areas. And it is right that often breakthroughs in science come from the boundaries between two fields, but not always. So often, for example, the DNA sequencing technology was extremely focused. First to sequence 10 or 20 bases, then 100 bases, then 1,000, then 1,000,000. So you're developing a fairly monolithic approach, different methodologies, but with the same idea. So again, you need both, the sort of very focused, in-depth, single field methodology development alongside cross-fertilization from other areas. Nobel Chemistry Committee said that they were going to give this prize for the development of the electron cryomicroscopy methods for determining the structure of biological molecules at high resolution. So people had been working for 20 or 30 years and getting structures at low resolution. So you could see your structures, but they were rather like blobs. And then they said that the electron microscopists were blobologists. They never got a good resolution. But as the methodology improved, we got from 2 nanometers to 1 nanometer to half a nanometer and so on. And eventually, when we reach a resolution of about 0.3 nanometers, about 3 angstrom resolution, then the features that you see can be recognized as being part of a protein or part of a nucleic acid. You see the individual amino acid side chains, and then you know what the chemistry is. So what Dubochet said is that you use physical methods to examine biological structures, and then as the resolution, when you finally reach a resolution of about 3.5 angstroms, suddenly you find you're a chemist, and you win a chemistry Nobel Prize, even though you know nothing about chemistry, because the structure you get sheds light and brings in, and so you then create a picture of how things are working, which integrates the knowledge. And that step from 5 angstroms to 3 angstroms is the big barrier which brings in chemistry, and then all the mechanism and all the function. So yeah.